Okay, can you see my screen?
Yes, sir.
Yeah, good morning
Yes,
to all
sir.
of you once again. Today's class we are going to discuss an important topic that belongs to module 5 called as active filters. Uh, Let me define what is active filter. Later on we can discuss on the types of active filters, how to design the filter, and where all we can use the filters, I mean the applications of filters. All those things we are going to discuss in today's class. Okay. So definition of filter. An electric filter, forget about active filter. Generally, an electric filter is a frequency selective circuit. The meaning of this circuit selects the frequency which we are intended, and that passes those selected frequency of a specified band of frequencies, and blocks or attenuate signals of frequencies outside this band. That means the band which we are not interested, those signals, the frequencies of those, the signals will be suppressed. The specified band of frequencies will be passed through the circuit. So that is the definition of active filter. An active filter is a frequency selective circuit that passes specified band of frequencies and blocks, I mean avoids or attenuates signals of frequencies outside the specified band. So this is the definition of electric filter. So having understood the definition of filter, let's discuss on the types of filters. Filters may be classified broadly into three types. There are numerous way of classifying filters. Mainly we can classify them into three types as follows: analog and or digital filters. This is the first way we can classify the filters. Passive or active filters, we'll see that later on one by one. Second classification is passive or active filters. Third way of classification of filters is audio frequency filter or radio frequency filter. Shortly, audio frequency can be denoted as AF, audio frequency. Radio frequency, which is usually higher frequency, radio frequency filters. So broadly we can classify filters into these three types. Now let us discuss one by one. What is analog filter and digital filter? Analog filters. These filters are designed to process only analog signals. So such filters are called as analog filters. On the other end, we have digital filters, where digital filters are used to process analog signals using digital techniques. Observe here, we are again processing analog signals only. We are filtering analog signals only. But the means we are using is digital techniques here. So such filters are called as digital filters. Okay, this is the first way of classification, first type of filters. Second classification is passive filters or active filters. So here, depending on the type of elements used in the construction, uh, these filters can be classified as passive filters or active filters. Here, we mainly look at the type of elements. The meaning of that is we can use resistors, capacitors, inductors, transistors, operational amplifiers. Among those elements, either we are using active elements or passive elements. Depending on that, filters can be classified into passive filters and active filters. Now, what is passive filter? A passive filters are those which uses passive elements such as resistors, capacitors, inductors, and so on. So these are the passive elements. Circuit which is constructed, a filter circuit which is constructed with the help of these passive elements are called as passive filters. Next, active filters. So today we are going to discuss more about these active filters. Active filters are those the filters that are constructed with the help of transistors. These are all active elements, or operational amplifiers. In our discussion, we are going to use mainly the operational amplifier along with the passive elements. See, active elements alone we are not using in the construction of active filters. Along with active elements like transistors or operational amplifiers, we are using passive elements such as resistors and capacitors in the construction of active filters. So that's the second type of classification of a filter. Third way of classifying filters are it's based on the frequency, the type of elements used, in the active filter that decides the operating frequency range. Okay. For example, RC filters, if I use resistor and capacitor combination, these are used only for audio frequency or low frequency operations here. So such filters are called as RC filters. Radio RC filters uses basically in low frequency applications here. Next category is LC filters, also called, or there are other type of filters like crystal filters, where we use crystal oscillator, crystal as a filtering circuit. So these, the LC filters are crystal filters, basically used at radio frequency or high frequency classification. Okay. So crystal provides more stable operation at higher frequencies rather than RC filters. Okay. In this chapter particularly, we do the analysis of filters, design of analog active RC filters are in the audio frequency range, basically using operational amplifiers. Inductors are not used in the audio frequency range, mainly because of the following reasons. Inductors are very large in size. The size of inductors is very large, and so that cannot be employed in audio frequency range. And moreover, the inductors are costly. They're not cheaper compared to capacitors and resistors. That's one of the reason for not using inductors in the audio frequency range. Third thing is inductors dissipate a lot of power. This is again a drawback of usage of inductors in audio frequency range. Lastly, inductors emit magnetic fields, so therefore we are not going to use inductors in audio frequency range. Before proceeding to the design of active filters, in today's class we are going to select only the active filters. The entire syllabus mainly focuses on active filters. Therefore, let us study the couple of advantages of active filters. Later on we can involve in the design of active filters. So the advantages of active filters are classified as follows. First thing is the reduced size and weight. This is the first advantage of active filters. All elements, with op amp, whatever you use, like resistors, capacitors, entire thing is available in integrated circuit form. Therefore, the size of entire active filters is going to be smaller, and of course the weight also it's going to be less. So that's one of the advantage of active filter. Active filters are of low cost due to availability in the integrated circuit form. Low cost in the sense that it's more economical because of absence of inductors in the active filters. That's the second advantage of active filters, low cost. Third advantage is active filters will have less attenuation. Only the specified band of frequencies they pass, and so there will be less attenuation. So the gain also can be controlled in the active filter in the closed loop fashion here. So there is a closed loop, so controlling that closed loop, the gain, the gain of the entire circuit can be controlled. The other advantage is active filters frequency adjustment is very much flexible compared to the passive filter, and it's very much easier to tune for whatever the frequencies we are intended to pass and we are intended to block, that can be easily tuned and adjusted in the active filters. So that such kind of frequency adjustment flexibility exists in active filters. Fifth advantage is there is no loading problem as such in the active filters because op amp used in the active filters. So we know that some important or ideal characteristics of an op amp, input impedance of an op amp is infinity, output impedance is 0. These ideal characteristics of an op amp will leads to no loading problem in active filter circuits. Okay. Active filters are realized under the functions such as Butterworth, Thomson, Chebyshev, and Carr filters. We'll study them in detail. So basically, these are the important functions we are using in the active filter design. So in our discussion, we use mainly the Butterworth filter, um, and remaining filter, rarely we use, in our discussion. Okay, so these are the functions we can use in the design of active filters. Response, there is active filters are has got improved response over the passive filters due to the high quality components. Op amp is again a very good component, very good circuit which is available in the form of IC package. Because of that, the response obtained from the active filters is an improved compared to the passive filter. And if you look at a design procedure of active filters, it's very simple. Okay, you need not worry about design, complexity. The complexity of design is very simple. The design is very simple here. Okay, active filters, we can use it for more gain and less attenuation. So these are the couple of advantages of active filters. Active filters also has got certain disadvantages. So very few disadvantages, of course. The first one is going to be the finite bandwidth of the active devices. So we know that we are using op amp or transistors in the active filters. These active devices has got some limit on the bandwidth. So that limits the high frequency operation. This is one of the drawback of active filters. Second thing is high sensitivity. Active filters uses active components. These components are very much sensitive to the temperature changes and environmental changes, humidity and noise, the disturbance, all those kind of things. So therefore, this poses another drawback of for the active filters because of usage of active components in the active filters. So therefore, they are highly sensitive. And the third disadvantage of active filters are active filters need DC power supply, whereas passive filter doesn't need this DC power supply. Okay, so this is another drawback of active filters. Now let us see the commonly used filters in our discussion. We use mainly the 5 different types of filters in our discussion. The first one is low pass filter. Low pass filter passes certain frequencies from 0 to some frequency. This is called as a pass band, and it blocks all frequencies above this frequency, say FH. So this is a stop band here. So this is the gain versus the frequency response of a low pass filter. High pass filter passes frequencies above this FL. If I call the cutoff frequency as FL here, above this frequency, the high pass filter circuit passes all those signals. From 0 to FL, the circuit tries to block it attenuates signal from 0 to say cutoff frequency FL. This is called as stop band. So stop band exists from 0 to FL, and pass band exists from FL to higher frequencies. Bandpass filter is the filter that has got the specified band of frequencies we are going to pass here, whereas we are going to limit all other frequencies. So pass band exists only in the for the selected frequencies. Remaining signals we are going to attenuate. So stop band exists at 2 places here. Okay, so this is band pass filter. Band reject filter is opposite to that of band pass filter. Here we are going to stop certain frequency of signals, and remaining signals we are going to pass here. Okay, so this is called band reject filter. We are going to reject signals between some frequency to in some frequency range. That's called as a stop band. Remaining signals we are going to pass here. So that's called as a pass band here. The signals of frequencies which we are going to pass is called as a pass band here. All pass filter, there is no limit, there is no question of your stop band. All frequencies this circuit is going to pass. So the commonly used filters are as follows: low pass, high pass, band reject, and band all pass filter we have seen here, and along with the gain frequency response. Okay. So active filters are extensively used in the field of communication and signal processing. Even today we can see that in almost all communication circuits and signal processing circuits we use active filters. Example is applications like radio, television, telephone, radar, space satellites, biomedical equipments. In all these places we use active filters. filters uses active element. In our syllabus we use op-amp as an active element in the active filter. Along with the active element, we are going to use passive elements such as resistors and capacitors here. So these two active elements along with the passive elements are the important components of active filters. So we can construct an active filter using op-amp. Along with op-amp we are going to use resistors and capacitors. Op-amp here mu A741, though this op-amp is a general purpose operational amplifier, this works satisfactorily in active filter, but in order to improve the performance we can go for high speed op-amps such as LM318 or ICL8017 op-amp. These are the high speed op-amps. If we use these op-amps as an active element, definitely the performance of a filter will be improved. The main advantage of this high speed op-amps is these op-amps LM318 or ICL8017 has got high slew rate and they have got high unity gain bandwidth. So because of these two advantages in this features of this op-amp, so these high speed op-amps can be employed in the design of in the construction of active filter circuits. Now let us see the frequency response characteristics of active filters. How exactly the filter behaves for different frequencies. Okay. In our analysis, we use dashed curve lines, to represent an ideal response. Solid lines we are going to use that represents practical filter response. So we have two types of response here generally: ideal response and practical response. To represent ideal response we are using dashed curves, and to represent practical response we are using solid lines. So from the frequency response we can understand whether it is a practical response or the ideal response. Frequency response means how exactly the circuit gain varies with reference to the frequencies. Okay, so for different frequencies, how exactly the gain of the filter varies, and that's called the frequency response. For different frequencies, we are seeing the gain of the filter. Okay, so how exactly it varies. So based on that, we can classify filters into. We have already seen the classification, but now we are seeing the characteristics of active filters. Let's consider low pass filter. Low pass filter is a filter, okay, which has got cutoff frequency of fH. For 0 to 0 hertz to fH hertz, fH is some number. The circuit is going to provide constant gain in this region 0 to fH, and bandwidth in this low pass filter is fH. Okay, so that's the bandwidth of this filter, low pass filter. At fH, at exactly this frequency, gain drops by 3 decibels. For the frequency greater than fH, gain decreases with the increase in the input frequencies. So I hope you understand the three categories here. For frequencies 0 to fH, low pass filter provides constant gain. From this we can calculate bandwidth of the low pass filter, which is fH in this case. At exactly fH, gain drops by 3 dB. So this 3 dB drop in gain can be used to calculate the bandwidth also. For the frequency greater than this upper cutoff frequency or high cutoff frequency, the gain decreases with the increase in frequency. If you try to increase the frequency beyond this fH, then such signals gain will be decreased here. Therefore, the passband exists between the frequency range 0 to fH. Stop band exists in the beyond fH. Okay, so these are the two things we need to understand in the low pass filter. Okay, the frequency response of this low pass filter is as shown here. The frequency response is plotted is a graph that's plotted again with reference to gain versus frequency. Gain is plotted along the y-axis, frequency is plotted along the x-axis. We can see here there is a frequency starting from 0 to fH, where we called as pass band. So frequencies from 0 to fH, those signals are passed, therefore that's called as a pass band. The frequencies above this fH are attenuated, so that's called as a stop band. And you can see here in the pass band the gain is almost constant, which is 1 in this case. So gain is plotted along y-axis, which is V0 versus V in. Okay. So gain decreases once we increase the frequencies beyond fH. We'll see that at what rate the gain decreases here. As we already told that this solid line indicate the practical response, dotted line shows the ideal response. Ideally, we expect filter to behave perfectly like this. At fH, exactly the signal should be attenuated. Beyond fH, signal should be attenuated. But from 0 to fH, exactly in this particular band, signals must be passed. Practically, that doesn't happen. Even beyond fH, the signals, certain frequency of signals are passed in the practical response. We can see that for some frequencies beyond fH, signals keeps attenuating. The circuit keeps attenuating those signals here. Okay, so this is the low frequency response of a low pass filter frequency response. Okay. Next, we'll see other. Before we go to the other filter, let us see the points covered under this topic. Figure 1, as just shown, represent the frequency response of the low pass filter. Ideal filter has 0 loss here, that's a pass band, there is no loss as such, and stop band has got infinite loss, that's what we have seen in the ideal filter. Stop band perfectly at fH, we have a stop band which we have got infinite loss. In order to make ideal filter response, in our case the ideal filter response is not equal to practical response, because there are a lot of discontinuities exist in various components that we use in the filter. Okay, so in order to make this ideal filter response equal to practical filter response, certain techniques can be followed here, certain methods can be followed here. Use of proper design techniques is one method to make ideal response approximately same as practical response. Second thing is use of precision components here, accurate components, exact components here, the components which has got high performance. Use of those components can certainly make our filter ideal response equal to practical response. The third method is use of high speed op amps. We already mentioned about two types of op amps which has got high slew rate and high unity gain bandwidth. Using those op amps in our filter circuits, so certainly can make our ideal response same as practical response. Okay. Next, as already mentioned about usage of functions such as Butterworth, Chebyshev and Core filters that are commonly used in the practical filter design that closely approximates to the ideal response here. What is so special about Butterworth filter? Butterworth filter, it has got flat pass band, that's one of the advantage for us, and even the stop band is also flat. Okay, so sometimes this Butterworth filter is also called as flat filter, and the design procedure is very simple. Butterworth filter design procedure is very simple, so that offers a lot of other features also. We will study those details in the upcoming classes. Okay. The second type of filter function what we use is Chebyshev filter. Chebyshev filter has got some ripples in the pass band. However, the stop band is going to be very much flat. Okay, so these are the features offered by the Chebyshev filter. Okay. The third filter which we can use practical filter is Core filter, where we see ripples in both pass band and as well as stop band. Chebyshev filter and Core filter we are not going to discuss in our this is not there in our syllabus. However, we are going to detail Butterworth filter design is discussed in our lecture. Okay. Next type of filter is high pass filter. So far we have seen the low pass filter and functions used in the low pass filter design. Now we are going to discuss high pass filter design and their frequency characteristics. High pass filter, the pass band exists with for the frequency greater than the FL. FL is called lower cutoff frequency. For the frequencies above FL, the pass band exists. Stop band exists between the frequency 0 and FL. Okay, so from 0 to FL there is a stop band. Beyond FL there is a pass band. Okay, F is called as operating frequency, and here we used FL. FL is called as low cutoff frequency. So we'll see these things with reference to the frequency response. So this is the frequency response of high pass filter. So stop band exists for the frequency in the range of 0 to FL. For the frequency above FL, there is a pass band here. These frequencies are passed. So this is the high pass filter. So therefore, the frequency above FL is efficiently passed without any attenuation. They are passed. Only the frequencies in the range 0 to FL are attenuated or suppressed. Okay, and we can also observe that gain keeps increasing as we move towards FL. So the gain of a practical filter keeps increasing. Beyond FL, the gain is almost constant. The analysis, in our analysis, we have seen that the solid line represents practical response, dotted line represents ideal response here. We expect high pass filter to behave in the way we are shown in dotted lines here. But practically, our high pass filter behaves in the form of solid line shown here. Okay, so this is the frequency response of high pass filter. A plot of frequency versus gain is called as frequency response. Okay. Next, we'll see the third type of filter, which is called as a band pass filter. As we already defined what is band pass filter, it passes frequencies of certain band and attenuates frequencies in the remaining band, in the remaining area. Okay, so this is a figure 3 that shows the frequency response of band pass filter. The frequency response is like the bell-shaped curve. Again, the frequencies are taken along x-axis. Gain is plotted along y-axis. Gain is an output voltage versus input voltage. We can also express this in decibels by converting this V 0 by V into 20 log of V 0 by V. Okay. So this is a band pass filter frequency response. We can see here there are two stop bands are there, stop band 1 and stop band 2. From 0 to FL there is a stop band 1. Once again there is a stop band 2 exists beyond for the frequency beyond FH. FC is called as a center frequency. This center frequency lies between the two stop bands. It's exactly in the mid of the pass band. Okay, so that's the center frequency where gain is going to be very high, which is 1. Unity gain is 1 in this case, exactly at the FC. Okay, as we move towards FL, again gain decreases, and again as we move towards higher frequencies towards FH, the gain decreases. Only at FC the gain is at unity. Okay, so we understood that the frequency range stop band 1 exists from 0 to FL, stop band 2 exists from FH onwards, and these frequencies between FL and FH, the circuit is going to pass the frequency line between FL and FH. So in this region we can see that the gain is almost like constant. Okay, so this is the frequency response of band pass filter. The same has been mentioned here in the points here. And bandwidth is FH minus FL. The difference between the higher cutoff frequency and lower cutoff frequency, that gives me the bandwidth of band pass filter. Okay. The observation here is that two bands exist in the band pass filter, and there is only one pass band, but there are two stop bands. Let us study the frequency response of band reject filter. Again, gain versus frequency response. If we observe here, there are two pass bands here, pass band 1 and pass band 2, and there is only one stop band here. we are going to reject frequencies in the range of FL to FH. And here the center frequency is the frequency we have taken where gain is 0. Okay, that's called as center frequency. Center frequency lies exactly in the mid of FL and FH. Okay, so in the passband we can see that the gain remains almost constant. Gain is almost constant even here in the passband 2. Again, there are two responses here: ideal response and practical response. Practical response is shown in the solid line form. Ideal response is shown in the dotted form here. Since there are two passbands here, there are two ideal responses in this filter, band reject filter. Okay. So if we drop by 3 dB, we can measure the bandwidth also. Okay. So this is 0.707 corresponds to the drop in 3 dB. So that gain range can be used to calculate bandwidth. So this is the frequency response of band reject filter. The explanation is given below. Stop band exists between the two cutoff frequencies FH and FL, and there are two passbands are there. Passband 1 is 0 to FL for the frequency 0 to FL is passband 1. Passband 2 is for the frequencies above FH. The band reject filter is also called by other names such as band stop filter or band elimination filter. Okay, so this is the explanation for band reject filter. The last type of filter that we are going to discuss here is all pass filter. This is a filter which passes all frequency signals. This is used in some applications. You will see the frequency characteristics of this filter. We are showing the frequency, the phase shift here. We are not going to show the frequency response in this all pass filter because it's going to be flat line for the gain versus the frequency. But here we show the difference between the phase shift between the input and output voltages for the all pass filter. All pass filter definition is it passes all frequencies equally without attenuating any frequencies. That's output and input voltages are equal in amplitude because it passes all frequencies. All frequencies for all frequencies there is a phase shift that exists between the input and output voltages that we have shown through the representation here. The highest frequencies up to which the input and output amplitudes remains equal is dependent on the unity gain bandwidth of an op amp here. We know that every op amp comes with certain unity gain bandwidth here. The highest frequencies up to which the input and output signals are passed with equal magnitude, it depends on the unity gain bandwidth product, gain bandwidth product of that op amp. Okay, so here we are showing the phase shift that exists between the input and output voltages. The blue color curve here sinusoidal shows the voltage, input voltage, and the red color line shows here the output voltage of output voltage. So you can observe here there is a phase shift between the output voltage and input voltage. So the phase shift is given as phi. Okay. So this is the phase shift which we are showing for the all pass filter between the output voltage and the input voltage. Now let us re-examine the filter and discuss important characteristics of the filter. If we re-examine the filter, the actual response curve of the filter in stop band, it steadily the increases or it may decrease depending on the type of filter we are going to consider. That's very important here. And another factor that we are going to discuss here is order of the filter. The order of the filter plays an important role here. So we may ask us to design a first order filter or second order filter like that. We'll see that what do we mean by order of the filter. Order of the filter is decided by the rate at which the gain of the filter changes in the stop band. So this is the definition of order of the filter. And order of the filter is the filter, the gain, how it changes in the stop band. Okay, at what rate it changes, that decides the order of the filter here. Let us see some examples here to understand what we mean by order of the filter. Example, say if we are designing a first order filter, say low pass filter, and we can see in the stop band at what rate the gain decreases. Based on that we can decide the order of the filter. Usually in the first order low pass filter, this is the frequency response of the low pass filter. In first order low pass filter, the gain decreases beyond FH. Gain should decrease for the practical filter. It decreases at the rate of 20 dB per decade, especially for the first order filter here. So that we can say that the gain rolls off at the rate of 20 dB per decade in the stop band. For the frequency, for the signals of the frequency greater than FH, the gain decreases at the rate of 20 dB per decade. This is first order filter. For second order filter, second order low pass filter, the roll off rate is going to be minus 40 dB per decade. That means the fastness, okay, the signal frequencies are attenuated at very high speed in the second order filter, because the roll off rate is going to be minus 40 dB per decade. Okay, the same thing can be applied to other filters like high pass filter. First order high pass filter, the roll off rate is going to be plus 20 dB per decade for the frequencies in the stop band for f is equal to fl. For second order high pass filter, the roll off rate is going to be plus 40 dB per decade until f is equal to fl. So this is the order of the filter. Order of the filter also plays an important role in the design. Okay. So that completes the order of the filter. Now let us have a look at first order low pass Butterworth filter. The first order low pass filter Butterworth filter circuit diagram is as shown here. We can see here we are using this is an active filter, of course. We are using op amp. Either you can use 741 or 351 or the op amp that I mentioned earlier. High speed op amps can be used in this place. That is a op amp is connected in inverting mode. So we can see here the input signals are provided to the non-inverting terminal of the op amp. So op amp is used in non-inverting mode. So input signal goes to non-inverting terminal of an op amp, and the capacitor here. The RC element forms the filter in this circuit here. So op amp is used in non-inverting mode of configuration. RF and R1 resistors here. This determine the gain of the filter. In this example, we are using both of them as 10 kilo ohm. Op amp has got implicit power supply like plus VCC as plus 15 volts and minus VES minus 15 volts. Okay, and we are using here potentiometer to control the frequency, the adjustment, tuning the frequencies we are using here, and the potentiometer here. Okay, and these two forms the filter here. R and C elements forms the filter here. So along with R and C as passive elements and active element as op amp, that forms a filter here. So this is a first order low pass Butterworth filter. Also we can observe here there is only one RC section here. Therefore this can be also called as first order. If we employ two RC sections in this path, so that filter can be called a second order filter, and obviously the roll off rate is going to be more, minus 40 dB per decade for the second order filter. Since this is here we have only one RC section here, this is R and this is C, so therefore this filter is first order. And the roll off rate for this first order low pass filter, already we have seen it is minus 20 dB per decade. Okay. So now let us see the frequency response. Already we have observed generally the general frequency response of low pass filter, but once again we are reiterating the same. So the voltage gain versus the frequency response is as shown here. There is a constant gain of an op amp is till 0 to FH. The filter provides constant gain. Beyond FH, the filter attenuates the signals. And as I already mentioned, this is a first order low pass filter. The roll off rate is going to be minus 20 dB per decade. So this is a frequency response of first order low pass Butterworth filter. Pass band exists from 0 to FH. So bandwidth is also FH. The signals frequencies within in this range are passed, so therefore it's called as a pass band. Frequencies above FH are attenuated, so that represents a stop band. Okay, so the explanation is as shown here. The figure 7 in this case shows the first order low pass Butterworth filter. Figure 6 shows the circuit diagram for the first order low pass Butterworth filter that uses an RC network. The resistance and capacitor combination forms the active filter along with the op amp, of course. Op amp is used in non-inverting mode. These are the observations one should make here. Hence, it does not overload the load the RC network here. Okay. Resistors like R1 and RF, which we are using in the feedback, that determines the gain of the filter in the pass band. Now, let us have an analysis of the filter. Analysis of the filter is very important because this helps us in understanding the design procedure for the active filter. So, we have seen that in the filter circuit we have an voltage divider rule can be applied for the filter circuit. The RC element that I have shown here, both are in parallel combination. So, the voltage at the non-inverting terminal, that is across the capacitor, is given by V1 equals minus J times Xc divided by R minus J Xc into Vn. Let us go back to circuit and try to understand this, how we get this voltage V1. Let us have a look at this circuit here. I am trying to determine the voltage V1 here. So, to determine the voltage V1 here, we can apply voltage division rule. Let us consider this as an impedance. There is a resistance here. So, these two comes in parallel combination. So, V1 is nothing but voltage at the non-inverting terminal. Voltage at the non-inverting terminal can be determined by applying voltage division rule here. So, V1 equals minus J times Xc, where Xc is the impedance of this capacitance, divided by R minus Jxc. Okay, so sum of these things. In this case, since capacitor impedance is minus Jxc, so that gets subtracted. R minus Jxc is in the denominator. That multiplied with the input voltage. I repeat once again, V1 equals V in times minus Jxc divided by R minus Jxc. That's the voltage at V1. Now, once we know voltage at V1, output voltage can be easily determined because this complete circuit is in non-inverting mode. We already know the gain of a non-inverting operational amplifier, which is V0 is equal to 1 plus RF by R1 times V1. So, to proceed to calculate output voltage, we need to know what is the voltage that's applied at non-inverting terminal. Once V1 is known, we can use the equation as V0 is equal to 1 plus RF by R1 into V1 here. So, that helps us in determining the output voltage V0. Now, let us see that V1 and let us simplify the V1 equation, and further we can proceed to calculate output voltage equation. So, we understood how we get this equation, minus J times Xc divided by R minus Jxc times Vn. This is by applying voltage division rule at the input of a circuit across resistance and capacitance here. Capacitor impedance is minus J times Xc, that we already know from the fundamentals, where Xc is called as capacitive reactance. Xc is given by 1 by 2 pi Fc. These are all fundamental things we are covering here. So, therefore, minus Jxc can be written as minus J divided by 2 pi Fc. Okay. So, minus J can be written as 1 by J, or minus 1 over J is equal to J. Therefore, if you replace this minus J as 1 by J, so minus Jxc becomes 1 divided by J 2 pi Fc. Okay. So, we can substitute this minus Jxc equals 1 by J 2 pi Fc in this V1 equation. So, let us see further how we can simplify this equation. So, V1 voltage at non-inverting terminal is now becomes 1 by J 2 pi Fc on substituting the equivalent of this minus Jxc, or minus Jxc value is 1 by J 2 pi Fc. Next, we can take LCM in the denominator as J 2 pi Fc. So, denominator changes to 1 plus J 2 pi FRC divided by J 2 pi Fc, that is multiplied with V. J 2 pi Fc cancels with the numerator J 2 pi Fc, and remaining terms are written here. So final equation for V1 is now equals V in divided by 1 plus j 2 pi f r c. Let us call this as equation 1. So far we have determined the voltage at non-inverting terminal. This can be used to calculate the output voltage. We know that op amp is used in non-inverting configuration. Therefore, output voltage equals now 1 plus Rf by R1 into V1. That's the voltage applied to non-inverting terminal. This already we have derived this equation. I am using directly the output voltage equation of non-inverting configuration. Now we can substitute from equation 1 the V1 here, and we can simplify further this equation. So V0 is equal to 1 plus Rf by R1. We can keep it as it is, but in place of V1 we have V in divided by 1 plus j 2 pi f r c. Rearranging this, we get and obtaining V0 by V in. So V0 by V in is now called as a gain of this low pass filter, which is equal to 1 plus Rf by R1 in the numerator we have, and 1 plus j 2 pi f r c in the denominator. We can introduce new terms here, and the final equation for V0 by V in becomes AF divided by 1 plus j f by fh. So we are calling this 1 plus Rf by R1 as a closed loop gain of the non-inverting configuration that can be denoted as AF. That's what AF is equal to 1 plus Rf by R1. So that's the gain of the filter in the pass band. And here fh equals 1 by 2 pi frc. So that's the upper cutoff frequency or higher cutoff frequency, that's labeled as fh. This f is kept as it is, and j also is retained. Remaining terms we are calling as denoting as fh. So therefore equation for fh becomes now 1 by 2 pi rc. So f is called as frequency of the input signal. This keeps varying. This is our x-axis parameter. Okay, fh is now 1 divided by 2 pi rc. fh is called as higher cutoff frequency of the filter. So we can decide to what range, to how much, to what frequency we can limit the signals. That's decided by the elements like resistance and capacitance. So V0 by Vin is called gain of the filter, which is a function of frequency now. Okay. So from this we can, from the equation, previous equation that we have derived, we can obtain gain, magnitude, and phase angle also can be determined for the low pass filter by representing the equation 2 in the polar form. Okay. So so gain magnitude now becomes V0 by V, the absolute value of that equals AF divided by root of its 1 square plus this 1 square remains as 1 only, F divided by FH whole square. This is the gain magnitude response of low pass filter. Phase response of low pass filter can be determined by obtaining the phase, which we call as phi, is a phase angle which is in degrees, which is minus tan inverse of F by FH. Okay, from the equation 2, you can use the phase of equation 2, that in the polar form that we get finally the phase equation as minus tan inverse of F by FH here. So the operation of the low pass filter can be varied from the gain magnitude that we have shown in the equation 3. How we can see that here, this operation can be verified actually. So at low frequencies we can see that when the F becomes very much less than FH, we can observe from this equation here, when F is less than FH, so complete term gets eliminated, and we are left out with just root of 1. FH becomes, FH is very large denominator part here, and F is very less, so this becomes redundant, so we are left out with root of 1. So the gain equation now becomes just an AF. Okay, this is equal to closed loop gain. The meaning of that is at very low frequencies, we have seen in the frequency response at this is a low pass filter. For a low frequencies, the gain is almost constant. For frequencies lying within FH, the gain is almost constant. What happens when the frequency applied frequency is exactly equal to FH, high cutoff frequency? So when the F becomes equal to FH, from this equation we can see here F, it is equal to FH, FH cancels here, and this becomes 1 here, 1 plus 1 becomes 2, this is root of 2. So the final equation of V0 by Vin is now AF divided by root 2, which is nothing but 0.707 AF. That means when the applied signals, of frequency f is equal to fh, the gain drops by 70% or 0.707 times AF. This is what we have seen from the frequency response also. We are cross verifying the frequency response from our gain magnitude equation. Lastly, for the frequency greater than higher cutoff frequency, what happens to this equation? We can observe here in this from this equation 3, for when f is greater than this fh, this value becomes larger, so that gain becomes less now here, because 1 plus this becomes a larger term here, root of that also becomes larger now. So therefore V naught by V will be lesser than the AF value. So this is the gain equation for the frequencies greater than fh. Okay. The following points will provide you more details of so far what we have discussed. For the range of frequencies lying from 0 to fh, gain is almost constant and equal to AF. In the fh range, its gain is almost constant, 0 to fh. At f is equal to fh, gain reduces by 0.707, which is equivalent to 3 dB down from here. This can be used to calculate the bandwidth. As the frequency increases beyond fh, the gain decreases at the rate of 20 dB per decade. This is a low pass filter, therefore gain has to decrease at the rate of 20 dB per decade. So 20 dB per decade, the meaning of this is there's a decrease in the gain by 20 dB for 10 times change in the frequency. This is the way we can define this role of break. Okay. So fh is called as a break frequency or a cutoff frequency or corner frequency. Okay. So we can call by different names here. Okay. So far we have discussed about the how exactly the Butterworth low pass filter works. We have derived the equation for transfer function V naught by V in, and we have cross verified our frequency response from the equation that we have derived here. So that's all about today's class, and in the next class we will see the exact design procedure along with examples, few worked examples we can take up in the next class. So thank you all very much. Thank you very much for your patience.